All right, so we're going to talk limits today. Start talking about limits. Interesting, not a super difficult concept, very, very useful. So here's a little example that we'll come back to, within a couple weeks and come to some resolution on this. But, we always want to talk about traveling to far off planets and distant galaxies and so on and so forth. However, when you look at the way that, for example, mass is affected by the speed at which an object travels relative to another object. This is called special relativity. It was brought to us by Albert Einstein. You see that we've got some problems because the relativistic, meaning for the traveler, the person that's moving at high speeds, at relativistic speeds, the relativistic mass is equal to the rest mass. So that what we would measure on Earth is a mass at rest, divided by what's called the gamma factor, the square root of 1 minus the velocity squared divided by the velocity of light squared. Okay, so what's the problem here? If we wanted to really get someplace fast and we wanted to, for example, go the speed of light, what happens to this function? Another way to write this would be to write this as m of v, right? Because v is the independent or input variable in this function. If we wanted to do something like calculate m, that's an m of c, what would I get if I evaluated that function at c? Well, v turns into c then, right? I'm substituting c in for v, for the independent variable v. So I would get m naught, m sub 0. Whenever we have something that's sub 0 like that, we call it naught in physics and math. So m naught divided by the square root of 1 minus c squared over c squared. Well, what's c squared over c squared? 1. 1 minus 1 is 0. Square root of 0 is 0. Okay, that's a problem, isn't it? We end up with an answer, m naught. There we go. Divided by, that's impossible. You can't divide by 0. Right? So what happens then? Well, you can't go the speed of light. That's the speed limit of the universe. Nothing with mass could ever go the speed of light. Okay, so we got to figure out some ways to talk about this more sensibly and make some sense out of this. We'll get there. It won't be long before we can come back and really have a better understanding of what's going on here. We could talk about it in a way that's going to be way more informative. Okay, let's leave this example for now, though. So let's talk about the concept of a limit. So we've got this function, f of x equals x cubed minus 1 over x minus 1. Well, we know how to evaluate a function. F of 3 would just be what? I'm going to get 3 cubed, so 27 minus 1 over 3 minus 1. So I get 26 over 2, so 13. Everybody agree with that? Give me thumbs up, thumbs down, thumbs sideways. We all good with that? Okay, so if I were to, for example, go into Desmos or go into a graphing calculator, and they haven't yet installed my graphing calculator emulator, so I can't do it myself anymore. So if we go into Desmos and we create this function, what happened there? Let's get rid of that. I'll tell you what I'm gonna do. I'm gonna cheat. I know on the next page. Yeah, there, I had one that already has that function on it. Okay. Well, look what I can do. I can plug in, I can use Desmos to evaluate this function. I can just go f of 3, and the answer is 13, right? And if I want to graph that point, I can just make the ordered pair 3 comma 13, or I can even do 3 f of 3, and there's my point. Okay, so it's just a point on the graph, no big deal. We're used to that, right? Okay. What about, okay, that was f of 3. What about f of 1? So I'd get Is it 0? If I try to evaluate this at 1, what do I get on the top of my fraction? What do I get on the bottom of my fraction? 0. Okay, so now what are our rules here? Our rules are, in math, we had 2 rules for real numbers you might remember talking about a couple of years ago. We can't take an even root of a negative number for real numbers, right? And in any case, for any complex number, we can't divide by 0, right? So this is not allowed. We can't divide by 0. So for this function f of x, x cannot equal 1. The function is undefined at f of 1. Everybody agree? Okay. It's undefined. Okay, but maybe we could do something more than just say it's undefined. Maybe we could ask ourselves, okay, well, yeah, it's undefined, but what value is the function approaching at 1? Okay. Let's see. Let's go to our graph and see. That's right, it's undefined. Yeah. So if we look on Desmos, if we go back here and let's change this f of 3 to f of 1, it's undefined. Okay. So if I put in the value 1, I want to map this point. X is 1 and y is equal to f of 1. Again, it's undefined. It doesn't even show up on there, right? If I trace along this graph, watch what happens when I get up to, oops, got to go down. Watch what, right there. Look, it says undefined. And look what happens on Desmos. I get this open circle there. Whereas if I move up to the right or down to the left, it's a solid point. When I go right to 1, probably can't do that again. I really like, oh, there it is. It's an open point called a hole in the function, and it's undefined. Okay, so properly to graph this thing, that's what it would look like. Now, that's one of the disadvantages of a graphing utility is it doesn't show you holes, right? Let me take a picture of this. Like that. So there's my picture. What I should do in my graph is I should up here at 1, 3. Oh, there's 1. Yeah, there we go. 1, 3. I really need to make a hole in the function that looks like that. Okay, that's an accurate graph of this function. The function is not defined at 1 because I can't divide by 0. Everybody see that? Okay, but what do you suppose if I were to do something like take this function and I want to do what we're going to call the limit of the function as x approaches 1. What does that mean, first of all? Well, what that means is this. We would say it, this is how we would say the words, that the verbal way of saying this math notation is the limit of f of x as x approaches 1. And the answer is, what do you think it is? If we go back to that picture that we had, right there, and let me copy that picture. I'm going to put it on the next page. So all that stuff. Let's make it a little smaller. Put it right there. What do you think the limit of that function is as x approaches 1? Any suggestions? What do you think? It's what? It's the answer is 3. How come? Because what? No, that's not why. That's an accident. That's an accident. How come it's 3? Okay, here's why. Because as the value of x that we're inputting into the function, as that gets closer and closer to the number 1, we're asking the question, what is the value of the function, meaning the y value, right? What is the y value of the function approaching? Okay, would you agree that it's approaching 3? Now, when I get to x equals 1, the function is actually undefined, but here's the most important thing to remember about limits. Limits, any questions so far? Let me pause for a second. Does that, I want to make sure everybody's okay with that concept. When we talk about the value of a function, f of x is just a fancy name for y, right? So the value of the function is always just going to be the y coordinate on a graph. It's the y value of the function, okay? As x approaches 1, what does approach mean? When you're approaching something, you're getting near to it, right? Like, remember this example we used to do in Algebra 2 a couple times? Like, if I'm walking towards my door, remember this one? If every second for eternity I cut the distance to the door in half, right? Do I ever get to the door? Never get there. But what's the only place, if I took a really fine Sharpie, like an infinitely fine Sharpie, and I made any dot I would choose to between me and the door, won't I always step on every dot that I make? Everybody get that? If the dot is not at the door, eventually, if I walk long enough, I'm going to step on every dot that I ever make, but I never get to the door, right? So what is the limit of my motion at this point? What's the point that I'm always approaching but never getting to? The door, right? Does that make sense? So that gives you kind of an idea of what a limit is. A limit is all about something you're approaching, but you never actually get there, right? As far as the limit is concerned, we don't actually care what happens at that point because we never get there. We just want to know, as we approach that point more and more and more closely, what's the y value that we're approaching, that we seem to be getting to, okay? So in this case, it's 3, isn't it? Isn't that the point that we anticipate getting to as we approach x equals 1, right? So the limit is 3. Doesn't matter that the function doesn't actually exist there, because when we're talking about a limit, you never get there. You just get as close as you want to, but you never take that last step. This is kind of a goofy way to think about it, but this really works for people. How to describe the flavor of limits. So imagine microscopic two-dimensional ants that live on functions in my Promethean board, okay? These ants are blind, but they have developed the ability to sense their position in the XY plane with perfect accuracy. So they always know exactly what their XY coordinates are when they're walking along functions. The limit of a function as x approaches the value c corresponds to the y value on which the ants would anticipate stepping. Where do they think they're going to step as they step onto x equals c? Okay, it doesn't matter what happens when they actually get there, but if you asked them when they're taking that last little itty bitty ant step, where are you going to land? That's the limit. Okay, so in this case, if we go back to this graph, well, the ants, as they're taking that last little itty bitty step, they're saying, yeah, I'm landing on the point 1, 3. Well, they don't. They disappear into some alternate universe in this case. I don't know where those ants go, but they're falling through a hole. That function doesn't exist there, right? Okay, give me 1 to 5. Does that make sense? Okay, so that's the concept of a limit. Questions? Questions? If you could articulate a question, it helps everybody. Yes. So C is just the value. In this case, C is 1. C is just going to be the x value that we're approaching. It just represents that. It could be anything. In this particular example, it's 1. Okay, so down here, we didn't want to pin this down to one value. We want to leave this very general, so we just say C, right? So we would say this: the limit of f of x as x approaches c is equal to L. In other words, L would be the y value that the ant thinks he's going to step on when he steps on x equals c. Okay? Okay, we'll get lots of practice with this. So to begin our exploration of limits, how do we calculate limits? How do we evaluate limits? Figure out what is the limit of a function? Well, the 2 ways we're going to start with are really, they're not analytical. They're just using kind of technology in a way. They're using graphs and tables. And then very soon we'll take another step forward to a more important technique, which is analysis using algebra. Yep. Well, okay, for now. Pretty soon we're gonna learn ways that we can do this algebraically and get exact answers where we're not relying on some graph. Because graphs aren't always easy to use, right? Sometimes, what if the limit is something really bizarre? Then it's difficult and time consuming to find out what the actual limit is. And what if it's an irrational number? You're never gonna know then, right? Okay, so there are some shortcomings to that, but it's a pretty quick and easy way to get an estimate of an answer. And sometimes that's all we need. If we only need the value of the limit to 2 decimal places, well, then that's great. Graph works fine. So does a table. And I'll show you how to do those both on technology today. Again, I don't have my graphing calculator emulator, so we're gonna have to come back and sort of backfill that in a couple days. Okay, but let's look at these examples. And we're gonna look at examples at and around x equals 2. Okay, so what about this first one, x squared minus 4 over x minus 2? Well, if I graph that function, that's what it looks like. Okay, and that not surprising probably, right? Because at x equals 2, I get 0 over 0. So is that always true? Do you always get, when I have 0 over 0, do you always get a limit do you always get a hole in the function? The answer is no, but usually. But you don't always get. I think we even said in Algebra 2 always, but I think I put an asterisk next to that. Said we'll talk about some instances in calculus where it doesn't happen. But the answer is not always. We have to do some further exploration. If I go back a second to this previous slide where we got 0 over 0, that's what we call an indeterminate form in calculus. Oops. And what that means is when you're trying to calculate a limit, that always means more work. So for now, the more work means drawing a graph or making a table. Very shortly, the more work is going to mean we have some calculus tricks for doing this, right? Initially algebra tricks, but then I'll show you a calculus trick that works really well pretty soon after that. Okay. Yep. Say it again. Okay, how do we know from the graph? Let's go to this example. How do we know from the graph? As x approaches 2, what's the limit of the function? 4. Okay, everybody see that? Because we're approaching this point right here. Even though this point is not part of the function, we're approaching the point with coordinates. Come on. 2, 4, right? So for this function, 2 is undefined, or the function's undefined at 2, but the limit exists because there is a place where the ant anticipates stepping, right? So we would say here the limit of the function for this example, the limit, oh my goodness, we just got started. Okay, we'll pick this up tomorrow.